Welcome back. So for the lecture today, for the lecture last time, we finished talking about kind of to the extent that we're going to talk about it, the algebraic structure of vector spaces. And really, what this means is its dimension. Okay. And so what we did last time was we finished our conversation about what a basis was by adding to our construction of linear independence of arbitrary vector spaces, the notion of a spanning set in an arbitrary vector space, and that led us to a basis, and that led us to a conversation about dimension. Okay, so now we're going to do analysis, not just algebra. Okay, and for us, that's going to mean norm. Okay, so we're going to recall the definition of a norm with a very mild generalization added, and then look at some examples. Okay. So first, let's recall what a norm is. So I mentioned we're going to look at a mild generalization, and so that's what I will do. A semi-norm for an F vector space B is a mapping. And the mapping takes a vector V and it maps it to the norm of V, which I'm going to write with double bar like that. And this is going to be a real number. And it has to, of course, satisfy some properties. So one, if I take a vector and I scale it, the constant pulls out with an absolute value. Okay, and so this is true for scalars F and vectors V. Okay, so that's a homogeneity property. And then there's a very important triangle inequality, which reads like this. Okay, and it's really the triangle inequality that makes for a lot of the kind of analysis that you can do using norms. And if additionally, we have this property that the only vector whose norm is zero is the zero vector. Okay, and so we know for sure that the zero vector has zero norm by this property. But if the only vector with zero norm is the zero vector, then the semi-norm is a norm. Okay. All right, so we're going to get things started by looking at a couple of typical examples. Okay, typical for us in what we're trying to do here. Okay, so there will be 9 examples, and they're going to come in 3 groups of 3. Okay, and the first sort of grouping is by vector space. So we're going to work with 3 different vector spaces, and then on each of those 3 vector spaces, we're going to consider 3 kinds of norms. Okay. So for the first vector space, we're going to take V equals Rn. Okay. And if you want, you could think of this as being also this. Okay, but for the purposes of the conversation here, we're going to use this representation. Okay, so that's the vector space, and here's the norms that we're going to consider. So the first norm we're going to call the 1 norm. And it is defined as follows. You take a vector V in Rn, and so remember that V is in Rn, so it's a ordered n-tuple of scalars. Okay, so that's the V that I'm talking about, and the definition of the 1 norm is that you take the sum of the modulus or absolute value, depending on whether you're working with, sorry, and I apologize, I did this again, switching between different lives. You work with the modulus or the absolute value, depending on the scalar field F. And so this is the 1 norm, and so I denote it with subscript 1. Okay, so let's see that this is a norm before we start looking at the other norms. Well, this one's obviously a norm. Okay, why is it obviously a norm? It's simply this property, the homogeneity property is clear. Okay, you stick a scalar in there and it's going to pull out with its absolute value. The triangle inequality is also clear, and that's just because the absolute value satisfies, or the modulus satisfies the triangle inequality. And it's also a norm because a sum of non-negative numbers is 0 if and only if each of the numbers is 0 itself. Okay, and so this is the upshot of that whole discussion, is that this is obviously a norm. Okay. The next example we're going to look at is what's called the 2 norm. And so we're going to see why 1 and 2. And so the 2 norm is defined like so. All right, so this is kind of the standard norm also. So if somebody says we're going to use the standard norm for Euclidean space, this is the one they're talking about. Okay, or sometimes also just the Euclidean norm. Okay. Okay, so is this a norm? All right, so let's look at the norm properties. This one's evident, right? So you stick a scalar in front of each of the components. It comes out with a square, and then the square gets square rooted. So you're good. The triangle inequality is actually the only one that's a little touchy here, and so if you've seen the notion of an inner product, which we will talk about later, but this is a norm which comes from an inner product, and the satisfaction of the triangle inequality follows from properties about inner products, including the Cauchy-Schwarz inequality. So we'll talk about why this thing is a norm, why this thing satisfies the triangle inequality later, but it also is a norm, not just a semi-norm, again for the same reasons that this one is. Okay, so this also is a norm. And we will verify the triangle inequality later. Okay. And then finally, the last of the three norms we'll talk about here is the infinity norm. Okay, and the infinity norm of a vector v in our Fn is defined like so. So you take the maximum size of the modulus or absolute value of the components of the vector. Like so. All right. Okay, so again, let's verify the norm property. So this one's clear. Okay, again, if you stick a constant in there, it pulls out with an absolute value up front. The triangle inequality, well, let's verify the triangle inequality. Okay, so we'll take two vectors, u and v, and look at their infinity norm. That's just the definition. Okay, so now we're going to use the triangle inequality in here for the modulus or absolute value. Okay. So now what we're going to do is we're going to change one of these indices here to something else. Okay, so this is going to be less than or equal to sup uj plus k, where j and k are. Okay, and this is true because if I think about what I'm suping over here, I'm suping over j and k. So the sup over all j's and k's, well, the sup here is over the case where j is equal to k. And so here, essentially, you're suping the same over a larger collection of numbers. And so the possibilities are that this one's going to be larger than the smaller, the suping over a smaller subset. Okay. And then you can then break down the sum there. Okay, the sup of a sum is less or equal to the sum of the sups. And this, of course, is just u, the infinity norm of u plus. Okay, so the infinity norm satisfies the triangle inequality, and it's also the case that this is a norm, not just a semi-norm. So satisfies this condition because a sup of a collection of non-negative numbers is zero only if all of the numbers are zero. Okay, So these are our three norms for the first vector space that we're going to look at. And these three norms, 1, 2, and infinity norm, we're going to be using more or less constantly throughout the term. And the 1 and the 2 here can be sort of generalized. And so maybe let me, sorry. Able to count using letters. And maybe let me, just while we're here, also define kind of a generalization of the 1 and the 2 norm, and that's called the P norm, because it's convenient to think about that. And because basically we're really mostly interested in the 1 and the 2 norm, but sometimes you can embed this in a larger family of norms called P norms, and it's just easier to talk about them both at the same time. And the definition of the P norm is this. Okay. And so you can readily see that when P is equal to 2, you get the 2 norm, and when P is equal to 1, you get the 1 norm. All right. Now again, the hard thing to verify here is the triangle inequality, and I'm not going to write this out. You can we'll look at inner products and we'll verify that the 2 norm satisfies the triangle inequality. But doing this is not a lot harder. It's fairly standard, but I'm not going to go through it here. But you can verify that this does satisfy the triangle inequality. Okay, good. So that's one vector space, and so I promised you 9, but apparently I'm going to give you 12 norms. The next vector space that we're going to deal with is this one. Okay, so remember we talked about this guy last time, and this is the mappings from J, a set J into F, so that F of J is not 0 for at most finitely many J. Okay. All right, so this was the vector space that we saw last time, whose dimension was the cardinality of the set J. All right, and it includes as a special case, of course, Fn. Okay. Okay, so let's write down the norm. So I'm just going to do this quickly now. So the 1 norm is, so I'm going to write an element of the vector space by F, because remember that elements of this vector space are functions, right? They're mappings from J to F. Okay. And the definition of the 1 norm is kind of the obvious adaptation of the 1 norm that I gave above for Fn. And it's like this. Okay. And so as I mentioned last time when we were talking about bases, this is an infinite sum, but it's a particularly nice infinite sum because it's actually only a finite sum, because for every F, there's only finitely many J's for which this is non-zero. Okay, so convergence isn't really an issue there. All right, so that's the 1 norm. The 2 norm is, again, the obvious adaptation to the definition I had above. Okay. And the infinity norm is okay. And so again, in this definition, that sum is finite, really. And so there's no problem with it converging. Here, again, only finitely many of these, as you run over all possible j's, are non-zero. And so this is a soup of a finite number of positive numbers. So that'll always be well-defined. It won't be infinite. Okay. Okay, so these definitions at least make sense. And then we have the norm, which includes as a special case of the 1 and the 2 norm, namely all the p norms. Oh, so I should have said here, p here is allowed to run from 1 to infinity. Okay, and that's so that the norm property is satisfied. And the norm property that requires this is the triangle inequality. So if p, let's say, goes between 0 and 1, okay, that will be a thing, but it won't be a norm. Because it will fail to satisfy the triangle inequality. But when p is greater than 1, it satisfies the triangle inequality. And it basically has to do with the fact that the graphs of the functions x to the p, for p greater than 1, it's convex, and for p less than 1, it's concave, or the other way around, whichever. Okay. All right, so the p norm here is the obvious adaptation from the definition that we had above for Fn. Okay, so these are all norms, and they're more or less just as easily verified to be norms as was the case for Fn. And the final vector space I'm going to look at is, one of the ones I've been kind of talking about lately. The continuous f-valued functions on the interval 0, 1. Okay, and now here, the role of the sum in the norms that we had here is going to now be played by the integral. Okay, so basically the norms look, the 1 and the 2 norm and the p norm look rather the same as they do for the other cases. You just replace sum with integral. Okay, so the 1 norm is so. Okay, and now to verify that the 1 norm is a norm is, again, very easy. You have homogeneity, obviously. If you stick a scalar in there, the scalar is going to come out front with an absolute value. Triangle inequality follows just because of the triangle inequality applied to the absolute value. And linearity of the integral. And this is also a norm, okay, but maybe we should think a little bit about why this is a norm and not a semi-norm, okay? So let's first make sure we understand why this number, this thing we're calling the 1 norm, is finite. Okay, so the norm should at least be well defined. And this has to do with the fact that we're working with continuous functions on a compact interval. Okay, so we know that a continuous function on a compact subset of Euclidean space, in fact, any compact subset, is bounded. Okay, and so what that means is that this thing will be bounded, and therefore because now I'm integrating a bounded function over a bounded domain, the integral will be finite. Okay, so this thing is well defined. Okay, that's good. So now let's think about why this is a norm and not a semi-norm. Okay, so let me not go through all of the details, but let me sort of sketch for you why this is so, because it's an argument that we're going to see kind of showing up in a few other places as well. All right. Okay, so suppose, and so what I want to do is I want to, so we want to show. So to see that this is a norm. Okay, and by that I'm focusing on, and not just a semi-norm. So it's the definiteness property that that when you apply this expression to a function, and if that's equal to 0, then the function must be 0. All right, so suppose that the norm, the one norm of f is equal to 0, but f is non-zero. Okay, so I'm going to arrive at a contradiction by doing this. Okay. Well, actually, sorry. Let me sort of change. I always try to be careful to not do arguments that are proving the contrapositive. It's easy to turn those into fake arguments by contradiction. This is one of those cases. It's actually, let's prove the contrapositive. So suppose that f is not equal to 0. Okay, so it's not the 0 function. Then what I'm going to show is that its norm is non-zero, which is equivalent to what it's the contrapositive of what I'm trying to show, which is that if the norm is 0, then the function is 0. Okay, all right, anyway, logic aside, this is my starting point. So f is a non-zero continuous function. All right, so what that means necessarily is that there's some x in 0, 1, so that f of x is not equal to 0. Okay, and so that's where you get to. And so let me sort of complete the proof by just a sketch. Okay. All right, so here's the graph of my function. Right, so I know that there's this point x where f is non-zero. And let me just, for convenience and to fix one of the two possibilities, let's suppose that f is positive. Okay, so so I know at this point the value of f of x is not 0, and I'm going to assume it's positive. Okay. Now we're going to use continuity of the function. And so what I know then is that there's going to be some interval around x so that the value of the function exceeds. So if this is f of x, okay, and this is a half f of x, okay, so that on this interval, the graph of the function lies above the value of the value of f at x. Okay, that's just by continuity. So it can't drop below 0, for example, which is really the thing I care about. Okay. And so let me write this little width here as r. Okay. And so what do I have? So I have that the one norm of f is the integral from 0 to 1 f of x dx. Okay, and this is going to be greater than or equal to the integral from x minus, let's say, r over 2 to x plus, and because I've decided to call this point here x, which I shouldn't have done, but now I need to recover from that. I'm going to put y inside, use y as the variable of integration. Oops. Okay, all right, good. So now I can use x in the limits of the integral. All right. Okay, so this is obviously true because this little interval here is going to be a subset of, the interval 0, 1. Okay, so I'm integrating the same function, which is the modulus of f, over a smaller domain. So therefore, this integral will be greater than that one. Or sorry, this integral will be less than that one. Okay, but I know, by the way I've defined r, I know that the value of f on this interval exceeds a half f of x. Okay, so this is 1/2 integral from minus x minus r over 2, x plus r over 2, f of x. Now dy, right? Because x is the point that I'm fixing here, and on the interval x minus r over 2 to x plus r over 2, f of y is greater than 1/2 f of x, right? So that's what this picture is. Okay. And so I do this complicated integral, keeping in mind that this is a constant for the purposes of the integral. And so this is equal to 1 r over 2 f of x. Okay, and this is positive. All right, and so that is what I wanted to verify, which is that if the one norm of a function is 0, then the function must be 0. Okay. Okay, good. Okay, so now we have the other flavors of norm for the space of continuous functions, the 2 norm. Okay, and now I'm just going to blast through this. So the definition here is kind of the obvious one. Okay, and again, this is well defined by the same reasons that I gave above. It's a norm, not a semi-norm, exactly by calculations like what I just did. And the triangle inequality, again, comes from the fact that this thing is a norm coming from an inner product. Okay, so it falls into the class of things which we'll talk about later in a more general setting. Okay, all right. Infinity norm. Okay. So you take the sup of the value of the function over the interval 0, 1. Okay, now this thing should be finite in order for this to define a norm, and it's finite for just the reasons that the 1 and the 2 norm are finite, namely that f is a continuous function, so continuity is important here, a continuous function defined on a compact interval, right? So it will be bounded, right? So we know that the sup is going to be finite. All right. It's obviously has the homogeneity property of a norm, and We also know that it satisfies the triangle inequality, and you can just construct an argument almost identical to that one to show that it satisfies the triangle inequality. Okay. And then you should verify also that it's a norm. Okay, and so again, that means that showing that if f is non-zero, then the norm is also non-zero, but that's obvious. If f is non-zero, then there's some point where this is going to be positive, and so this supremum is also going to be positive. All right. And finally, we have the p norm, which generalizes the 1 and the 2 norm. And again, p is required to lie between 1 and infinity. Okay. And it's f p. It's interval from 0 to 1, f of x to the p dx. Okay. All right, so these are the kinds of norms that we're going to be encountering throughout the course. All right. And what we're going to do is we're going to study in some detail the property of spaces with norms like this. Okay, and what are those properties that we might study? Okay, well, there's a primary property of interest when we're talking about normed vector spaces, and that property is the property of completeness. Okay, so all right, and so I haven't defined it formally, but it's obvious what a normed vector space is. A normed vector space is a vector space with a norm. Okay, you can also, of course, talk about semi-normed vector spaces. And semi-norms are going to come up in a couple of ways for us. One way is that we're going to see in our constructions in a while that there's a natural thing which we'd like to be a norm that arises, but fact is it's not a norm, it's a semi-norm, and so we have to do some stuff to turn it into a norm. Okay, that's one way that a norm is going to arise. Another way that a norm can arise that a semi-norm can naturally arise is something we won't see until significantly later on, when we're going to sort of look at spaces of signals which don't admit naturally a norm, but which we can describe not by just a semi-norm, but by a collection of semi-norms. Okay, so that, but that'll come later. All right. Okay, excellent. So what is completeness? So let's give some definitions that frame this discussion of completeness, and then we can talk about kind of what it means. So completeness has to do with sequences. All right. Okay, so I have a normed F vector space. F, of course, as always, is R or C, and I have a sequence in this normed vector space. The sequence converges to some vector V naught, let's say, in V, if, okay, for every epsilon, positive, there exists some positive integer n so that Vj is within epsilon of V. Okay, so you should think of a norm as, kind of giving you a notion of a distance. And so the distance of Vj from V0 is less than epsilon for large enough j, is what this is. Okay, and so the idea is the usual notion of convergence that you're familiar with, that the terms at the tail of the sequence can be made to get as close as you wish to the vector in this case that you're converging to. Okay. So that's convergence. Another important notion, which is related but not the same to convergence, is what's called a Cauchy sequence. Okay. And so the idea of the definition here, so for convergence, the terms in the sequence were getting close to some fixed vector, which is the limit of the sequence. Okay. Here, we don't have a limit, but what we have is we have that the terms in the tail of the sequence. Oh, so sorry, I need to say that k is also has to be greater than or equal to n. Okay, so the terms in the tail of the sequence, Vj and Vk, they get closer and closer to each other. Okay, so the question you want to ask here is what is the relationship between convergent and Cauchy sequences? Okay, well, one half of the relationship is clear. And that is the convergent sequences are Cauchy. Okay, so this is easy to prove, and you almost certainly proved this in your analysis course, but let's give it in a slightly more general context here of an arbitrary normed vector space, not just say Euclidean space. Okay. And so I'm going to show that it's Cauchy. So that means that I need to show that for every epsilon, there exists an n. Okay, so I need to choose epsilon. Okay. Now, I need to find an n. So here's how I'm going to choose n. So let n so I know that my sequence converges. And so I know that, and so I should say this false, but I'll say it in a second. Okay, so I know that my sequence Vj converges, and so it's going to converge to V naught. All right. And so I know that therefore there exists an n, so that this okay, the distance between Vj and the limit V naught is less than epsilon over 2 for a large enough j. Okay, so that defines my n. Okay, so then Vj minus Vk is less than or equal to Vj minus V naught plus V naught minus Vk. Okay, and this is where the triangle inequality helps you. So this is Vj minus V naught plus Vk minus V naught. Okay, and okay, and I've chosen, and so here I'm going to take j and k greater than or equal to n, in which case, by the way I've chosen n, I know that each of these is less than epsilon over 2. Okay. All right. Oops. All right. So now, what about the opposite implication, namely the convergence of Cauchy sequences? Well, that's not generally true. And we're going to explicitly build examples of non-convergent Cauchy sequences so we can get some feeling for what the problem is. Okay, so have you seen one before? Well, probably not. And the reason is the following. And again, you would have proved this in your analysis course. Okay, you would have proved this for Fn, say, or Rn maybe, with some particular norm, say the 2 norm, the standard norm. Okay, but it's a slightly more general thing is true, and that is this, that if V is a finite dimensional normed vector space, then every Cauchy sequence converges. Okay. So therefore, if you're going to find an example of a non-convergent Cauchy sequence, you're going to have to look for an infinite dimensional normed vector space. Okay. All right, so let us, therefore, do exactly that. Let us give an example of a non-convergent Cauchy sequence in a suitable infinite dimensional normed vector space. Okay, so I'm going to take the normed vector space V equals F I'm going to take one of these f to the j sub-zero vector spaces, but I'm going to take this special case that we talked about a few lectures ago now, where the set J is the set of positive integers, right? So this is what is this space? So this space is going to be mappings from the positive integers into F, where at most finitely many, where the mapping vanishes, except on at most finitely many of these positive integers. Okay. Now the notation I'm going to use for this, because it gets cumbersome writing a superscript of like that. Okay. I'm going to write this as F infinity 0. Okay. The infinity, kind of meaning that there's infinitely many terms in the set that you're mapping from here. Okay. Right. But in any case, that's the notation that I'm going to use. Okay. Okay, and what's the norm that I'm going to use? I'm going to use, for the purposes of this example, we'll look at other norms for the same example later, but we're going to use the infinity norm to start out with. Okay. All right, so it's going to be helpful to think carefully about what that space is. So we decided that without the 0, okay, that this space was the space of all sequences. Okay, now the 0 here enforces a condition that only finitely many terms in that sequence can be non-zero. Okay, so if you have a sequence of scalars from F, and only finitely many of them are non-zero, what that means is that after some term in your sequence, all the remaining terms in the sequence are 0. And so the way that you can think of this space is that this is the space of sequences that are eventually 0. Okay, and you have to be careful. I don't mean they're converging to 0. I mean that they're eventually identically 0. So after some index, a sequence in here, after some index will vanish identically. All right, so the tails of the sequence aren't small, they're 0. Okay. Okay, good. So I'm going to build, as I said, a non-convergent Cauchy sequence in the space of eventually 0 sequences. Okay. All right. So a term in this sequence, of course, we think of sequences as being mappings, right? So, it's a mapping from the positive integers into F. All right. And so we're going to define a sequence. And the sequence is going to be, I'll write it as Fj in F infinity 0 as follows. Okay, so Fj of K, all right. Okay, because Fj is a mapping from the positive integers into F, and so the argument of this function is going to be K. Right, and here's how this thing's going to look. So it's going to be 1 over K, right, where for K's between 1 up to J, and it's going to be 0 otherwise. All right. So let's try to understand what these things, what these sequences are. These sequences Fj, Okay, so this is, it's a little bit confusing possibly here, and that's why it's better to think of these things for some purposes at least as not as being sequences, but as being functions, because then we have a sequence of functions. Otherwise, you have a sequence of sequences, and it gets confusing. Okay. Okay, so let's understand these functions by graphing them. Okay. Okay, so here's k out here. So here's k equals 1, 2, 3, 4, and so on. All right, and here's let's graph f1 of k. All right. So what's the definition? The definition is, right, so this k is going 1, 2, 3, 4, and I'm fixing j here to be 1. All right. And so at f1 at k equals 1, okay, is going to be 1 over 1, which is 1. Okay, so it's going to take and I'll graph the sequence just by kind of doing this. I'll put a little dot there to indicate the value of the function at the point 1. All right, so that value there is 1. Okay, and then f1 is going to be 0 for all k's larger than 1. All right, so it's 1 there and then 0 everywhere else. Okay, let's look at f2. Okay, so f2. So now I take k equals 1, and again, it'll have the value 1. So it looks like f1 here. Right? And then at k equals 2, it has the value of half. So the value here is half. Okay, so and then it's 0 everywhere else. All right, so it becomes pretty evident what's going on here. But I'll add one term to this just to make sure I hammer it home. Okay, so f3 will have a value 1 here. It'll have a value a half here. And it'll have a value a third here. And then 0 forever after. Okay, so certainly we can see then that fj is in f infinity 0. Okay, so the main thing being this. So it has only finitely many non-zero terms. Okay, good. All right, so now claim. I'm going to first show that this is a Cauchy sequence. Okay. All right, so to show that it's a Cauchy sequence, what I have to do is I have to choose an epsilon, and then I have to think about the norm of fj minus fk. All right. So really what I need to do to understand what's going on with the Cauchy sequenceness of this is I have to think about fj minus fk. All right, so let's do that. Okay, so all right, so I have So here I'm going to now here I used k as my independent variable. Well, I'm going to also use k for my Cauchy sequence fj minus fk. So here I'll switch to using m. Okay. All right. And so what I'm going to plot here is I'm going to plot the function fj minus fk. All right. And I'm going to assume that k is greater than j. All right. Okay, good. So now so here I have, let's say, 1 and 2, and I'm sort of go along here until I get to j. Okay, and so let's see what happens with fj minus fk here, because j is the first one I'm going to come to. Right. All right, so up until here, so I also have j minus 1. Okay, so certainly up until j minus 1, fj and fk are going to assume the same value, right? Just I can see that in my sort of plots up here. F3 and F2 agree up until 2. Okay, and so that means that up until J, Fj minus Fk will be 0. Okay, and then at J plus 1, okay, suddenly now fj is going to be 0, and so the only thing that I'm going to have is I'm going to have fk, and so therefore, so I always have to adapt this as I go along. Okay, so just to keep things positive, let me look at fk minus fj. All right, so for at j plus 1, fj is 0, but fk is going to assume some non-zero value, and that non-zero value is going to be 1 over j plus 1. Okay, so fk will have some value, fj will be 0, and the value here will be 1 over k plus 1. And similarly at j plus 2. Okay, and it'll decrease to be, sorry, that's not, I apologize. That's 1 over j plus 1. The value here is 1 over j plus 2. And I keep going, okay? And I sort of go along out here until I reach k, all right? And then the value here of fk will be 1 over k. And then forever after, k plus 1, k plus 2, and so on, the value of fk minus fj will be 0. Okay, all right, so let me sort of summarize that. Because fj and fk agree up until the argument j, it's 0, then suddenly at m equals j plus 1, fj vanishes, but fk will be non-zero, and at j plus 1, I'll have the value 1 over j plus 1, at j plus 2, I'll have the value 1 over j plus 2, all the way up to m equals k, and then at this point, fk will have the value 1 over k, and then forever after I'll be 0. Okay, so this is the thing I need to understand in order to understand how this thing is a Cauchy sequence. Okay, good. So now that I've kind of drawn the graph of this thing, it's easy to see how this is a Cauchy sequence. You can just see it from the graph. If you choose j and k large enough, the largest value of this function is going to be 1 over j plus 1. Okay, and by choosing j large enough, and therefore also k large enough, that can be made as small as you like. All right, so now it just remains to go through the formalities. Okay, so let epsilon be positive and choose n so that 1 over n plus 1 is less than epsilon. Okay, then fk of m minus fj of m. Okay, so it's this m here that I'm talking about. Okay, will just by and so here I'm going to so I'm going to be thinking about k and j greater than or equal to n, right? And so what that means is that 1 over j plus 1, okay, which is this term, is going to be less than or equal to 1 over n plus 1, which is less than epsilon. Okay, so this is, and I'm also going to take, just as I did above, k to be larger than j. Okay, so I'm going to, in summary, I'm going to choose n this way. I'm going to choose k and j larger than n, and I'm going to assume that k is greater than j. All right, and upon doing so, my graph drawing skills up here give me that this is less than 1 over j plus 1, which is less than or equal to 1 over n plus 1, which is less than epsilon. Okay. All right, so that shows that it's a Cauchy sequence because by taking j and k large enough, I can ensure okay, that this is true. Okay, but it's because this analysis, this holds for every m. Okay, that's what my graph here shows, right? So this is true for every m. Right? And if it's true for every m, then the infinity norm also satisfies that inequality. Okay, good. So that's a Cauchy sequence. Again, if you sort of draw the graph, it's immediately clear. All right, now I should show that it doesn't converge. All right. And how am I going to prove that? Okay, well, what I'm going to do is I'm going to assume that it does converge, okay, and I'm going to arrive at a contradiction, okay. Okay, so first, so suppose that the sequence does converge. Fire somewhere. Okay, so it converges to some f. So I claim I take an m and I fix an m, and what I'm going to do is for this m, I'm going to claim that f at m must assume some value. Okay. And of course, the value is going to be this. It just, if you sort of eyeball this, what's going on with these plots of these functions fj, that's kind of the obvious thing. Okay, right. So I'm fixing an m, and then I'm going to prove that f at that m has to have that value. Okay, so suppose not. Okay, so I'm going to say that that difference is non-zero. Okay, all right. So okay, so now how do I arrive at a contradiction from that? Well, what I'm going to do is I'm going to use the fact that this is the limit of these guys. Okay. All right, so then, okay. All right, and so what I'm going to do is I'm going to show that if I assume this, then I'm going to show that it cannot be the case that this converges to that. Okay, okay. So then for let's say L greater than M, okay, we sorry, let me. Okay, so I'm going to prove that it contradicts the convergence criterion. Okay, and so what I'm going to do is I'm going to calculate F minus Fj in the infinity norm. Okay, and so I can do this for large J because I'm interested in convergence, and so that's really only this is only really interesting for large J. So I'm going to assume that J is greater than M. Okay. So if J is greater than M, greater than or equal to, I guess, okay, then what's this expression going to be? Okay, well, let's just write down the definition. So it's sup F of L minus Fj of L, where L is in my index set. All right, so that's the definition of the infinity norm. Okay, now in this sup, okay, is contained that, right? Because I'm assuming that J is greater than or equal to M, and so I know that at L equals M, Fj, right? So Fj's are these. Okay, so I know that at L equals M, Fj has the value 1 over M. Okay, so this is greater than or equal to F of M minus Fj at M. Okay, right? So that's true just because I've taken I'm souping over a bunch of numbers, and so that soup is obviously going to be greater than or equal to any of the particular numbers that I'm souping over. Okay, so I'm choosing the one where L is equal to M. Okay, and now as I said, because J is greater than M, this thing is equal to F of M minus 1 over M, because that's the value of Fj at M, okay, which is equal to this number beta, which is greater than 0. Okay, and so the point is that this is true for every J greater than or equal to M. Okay, and so therefore this contradicts convergence. Okay, and it must therefore be the case that this holds. Okay, so I've done this argument by fixing an M. Okay, so I fixed an M, and then I proceeded to show that this must be true. Okay, now I'm going to free M because this argument can be repeated for every M. Okay, so what have I done? So I've shown that starting from the assumption that fj converges to f, right? So f is the limit of the fj's. Okay, so first I showed that for a fixed m, f of m must be equal to 1 over m. Okay, and I did this by contradicting convergence. And then now, because m is arbitrary, I must have that if fj converges to f, then f satisfies that equation for every m. Okay, but this immediately implies that f is not in is not in f infinity 0. Okay, and so therefore my assumption that I started out with, that this sequence converges in here, is false. Okay, so this is an example of a non-convergent Cauchy sequence. Okay, and it's kind of clear what's going on here, right? The problem is not with the sequence itself. The sequence seems perfectly fine, right? The sequence seems to happily be converging to this. The problem is the space in which I'm talking about convergence, right? And that this space seems to have this property that there are Cauchy sequences in here which happily want to converge, but the thing that they want to converge to is not in the space. Okay, and so this leads to the notion of completeness, but I'll pick up the discussion there next time. I mainly wanted to give an example, a simple example of a non-convergent Cauchy sequence. Okay.